Okay, these are some more problems from section 9.5, and this is number 23. And on these problems, we want to determine whether the series converges absolutely, converges conditionally, or diverges. It says give reasons for your answer, and then find a bound for the truncation error after 99 terms. Okay, so this was a series. It's an alternating series, but what I'm going to do is I'm going to check for absolute convergence first, because if it converges absolutely, then we know it converges, and then we don't have to worry about conditional convergence. So I'm going to do that. I think that's probably the safest way to go in the long run. All right, so this is my series, and I took the absolute value of it to check for absolute convergence. And that just gives me this series. Now, the nice thing about this, I'm checking for absolute convergence. Okay, 1 plus n over n squared. It's real easy to compare that to n over n squared. We know that this is bigger than that series, because the numerator in this fraction is bigger than the numerator in that, and the denominators are the same. But I can reduce this to be 1 over n. This is the same thing as 1 over n. And I know that this diverges by the p-series test. It's actually the harmonic series. So I can say that this diverges by the direct comparison test. All right? Direct comparison. Because the series that it's greater than diverges, so it kind of pushes it up. So it also diverges. So it does not converge absolutely. Okay? Now we have to check the series to see maybe it converges conditionally. Or it could just diverge overall. So let's take a look at this, and this is the B part. This is what I would do secondly. And I'm going to check the series in its native form, not absolute value. And it's an alternating series, so if we look at our alternating series test, our U would be 1 plus n over n squared, because this is the alternating part. And for n greater than 1, I think you can see that U sub n is greater than 0. I think that makes sense. Now, this might be a little bit harder to see that it is decreasing, that as n gets bigger, this actually gets smaller. But we'll show you that in just a second. We've got a better way to show that. And then also the limit as n approaches infinity of U sub n is equal to 0. So let's take a look at that possibility also. This limit, well, we could take that limit and see. It looks like I've got n over n squared, so it looks like that as n goes to infinity would become 1 over n, which would be 0. So it looks like that's okay also. But just if we want a formal way of checking these things, just so you know that you can possibly do this, let's check for the decreasing part. Okay, we're pretty much sure that this is going to be positive. That's no problem. Okay, in order to see if it's decreasing, if we look at the function that describes the terms of the series, if the derivative is negative for all values of x, that means it's decreasing. So that's another way of showing it. So let's take the derivative of this, and we'll use the quotient rule. Okay, low d high, less high d low, denominator squared below. And we get x squared, and then negative 2x, and negative 2x squared, all over x to the fourth. And then I could simplify this. X squared minus 2x squared is negative x squared. So I've got negative 2x squared minus x squared all over x to the fourth. And I can factor out an x and simplify, and I have this. Now remember, x is going to be greater than or equal to 1, so this is always going to be positive, and this will always be negative, and that's negative. So this will always be less than 0 for all x greater than or equal to 1, which is part of my summation. That's n in that case. So that's another way of showing it. F is decreasing, so our series is decreasing. And you could look at it intuitively and say, well, you know, as n gets bigger, this is going to grow faster than the top, so the bottom grows faster than the top, so it would be decreasing. You could do it like that. Now, how about the limit? Well, we could take a look at this limit, and as 1 plus n over n squared, the limit as n approaches infinity. Well, if we substitute, we get infinity over infinity, so we can do L'Hopital's rule, and that's going to be 0, and that's going to be 1, and this is going to be 2n. If we take the limit of this as n approaches infinity, we get 0. So this is a little more formal way of doing that. If you're not too sure, you can try these methods, and this will help show that this series and the alternating series meets these three criteria, so therefore the series converges by the alternating series test. All right? So it converges, but not absolutely. Okay? So what does that mean? So we'd say letter C, and like I said, I did these in kind of a funny order. Letter C, this is my series. It converges conditionally because it converges but not absolutely. All right, so that's conditional convergence. Not absolutely, but it does converge. Okay? And then the error after 99 terms, by theorem 13, it's less than the 99 plus first term, or the 100th term. So U sub 100 is just 1 plus 100 over 100 squared. And if you work that out in your calculator, you get 0.0101. So it's the first, what we call the first unused term. Okay? Okay, number 24. This is my series, and right away I just tried to check it for absolute convergence. Now, if we look at this, if we look for absolute convergence, check for absolute convergence, we have the summation 1 over n to the n. I wrote the 0.1 to the n as 1/10. And this is a geometric series, and what's r? R is going to be 1 over 10. That's my ratio, and that's less than 1. So this series converges absolutely. So we don't have to say anything about conditional, because it converges absolutely. All right? And after 99 terms, if you work this out on your calculator, it's 0, so it's best just to leave it in this form, because it just rounds off to be 0. Our calculators don't go out that far. So after 99 terms, I would just put, this would be to the 100th, this would be U sub 100, so it'd be 1 over 10 to the 100th power. And that's the error. Okay. Hope those help.